So now we're moving to the next stage of statistical and advanced statistics. So this is important. Sometimes you get an EMI with 5 options. Sometimes you can have 1 or 2 questions. If you're lucky, you will have just 1 or 2 questions. If you're really having hard luck, you will have an EMI asking you to choose statistical tests. Now, it's not as complex as it sounds. Whenever you have an exam question where they give you a scenario, a research scenario, and they ask you to choose appropriate statistical test, you need to stop, think, and try and answer 5 questions in your mind. If you answer these 5 questions, depending on the answers you get, you can easily choose a statistical test, because for each set of answer, you have only 1 statistical test that you can choose. Okay, so I'm going to show you what those questions are and what the answers are, and how to choose statistical tests on this basis. First question: how many variables are being compared? Okay, so what do I say by how many variables? Let's take the example. This webinar. Let's say there are males and females attending this webinar, and I'm interested in the age, the average age of males and females here. I'm going to compare the average age of males with the average age of females. So how many variables am I interested in? I'm only interested in 1 variable. That's age. As simple as that. If I want to look at the relationship between age and paper B score in the 2 groups, now how many variables am I interested in? 2 variables. One is the age, one is the paper B score. Okay, so this is how you look at the number of variables. Number of variables that you are interested in. That's the first question. How many variables are you interested in? In most situations, we are only interested in 1 variable at a time. So it's called univariate analysis. Okay, sometimes we're interested in 2 variables, a relationship between 2 things, and that's called bivariate. Sometimes we're interested in multiple variables. So you want to know what is the cause, what is the effect, and you also want to know what is the confounder and what is the effect of confounder. So whenever you have a 3rd variable, confounding variable, you are dealing with multivariate statistical tests. Okay, so that's the first question: how many variables? And based on that, you choose either a univariate test, bivariate test, or multivariate test. Second question: how many groups? How many groups are you comparing? So if I'm comparing age of males versus age of females, how many groups do I have? Only 2 groups, male group and female group. So that's how many groups. If I'm comparing the age of, let's say, people who attend webinar today, people who attend webinar a week later, and people who come to people who take online course. So I have 3 groups: people who attend webinar today, people who attend webinar next week, and people who attend people who take the online courses. So you'll have 3 groups in this situation. Okay, now sometimes I may have same set of individuals, but they occur in 2 different groups. Let's say, for example, I take all of you today and I do a mock exam for you, and I find out how much you score. So I have an average score, mock exam paper B today. I teach you something for 2 to 3 hours, and then I do another mock exam for you. And in this time, you score some other, well, you improve your scores, let's say, and you have another average from the mock exam 2. Now I want to compare the mock exam 1 score with mock exam 2 score. How many variables am I interested in? Only 1 variable, mock exam score. But how many groups do I have? I have a group that took the mock exam before the intervention, that's my lecture, and that took the mock exam after the intervention, that is after my lecture. Okay, well, same set of people, but you form 2 set of observations, and that's why that's what we mean by groups. When I say groups, I mean how many times a collective observation has been taken. Okay, so 2 groups. These are called paired observations, because same group is observed twice. So the score that you, the amount of the marks that you get for mock exam 2 will depend on the marks you got for mock exam 1. Can I say that? Yeah. People who are scoring high for mock exam 1 will score high for mock exam 2 as well. So there is more pairing among individuals when I do observation 2 times on same set of people. That's called a paired observation. Okay. Instead, if I compare the mock exam 1 score of males versus mock exam 1 score of females, I have 2 different groups now, and these are independent observation, because a male person's score is not going to be influenced by a female person's scores. These are completely different groups. Okay, so in the first example, when I do mock exam 1 and 2 in the same set of individuals, that observations are paired. If I do mock exam 1 in two different groups, that becomes independent observation. Is that clear? So that's the third question, independent or paired. That depends on how many times a single variable is measured in each individual. Okay, mock exam score is the variable. If I measure that variable only once and I compare two groups, it's independent. If I measure that variable twice in same individual and I'm going to compare those two scores, that's called paired observation. Okay, as simple as that. So the question you have to answer in your mind is, a single variable, how many times has it been measured in a single individual? If it is measured more than once, you are looking at paired tests. Okay, so that's the third question. There are a group of tests called independent statistical tests, group of them called paired statistical tests. So depending on whether we do independent or paired observation, we'll apply them. So we've done 3 questions, question 1, 2 and 4. What about 3? Parametric or not? Now you know the answer for this. Any distribution that is normal, you will apply parametric statistical test. Any distribution that is not normal, for example, if you have a skewed distribution, you will use non-parametric tests. If you have ordinal variables, ordinal means it is not quantifiable, it's qualitative. So ordinal variables, you can only use non-parametric statistics. So whenever you have continuous normally distributed data, then you will use parametric. Okay. Finally, what are you comparing? Are you comparing mean values or are you comparing frequency count? So if you put people into boxes, categories, responder, non-responder, people who commit self-harm, do not commit self-harm, that means categorization. If you do categorization, you can put people in 2 by 2 boxes. When you do 2 by 2 boxes, you are having counts. You are counting how many people are in each box. So in that case, you are comparing frequency counts. You're comparing proportions. Okay. When you compare proportions, you have a different family of statistical tests you can use. When you compare mean values, you can use a you'll use a different set of statistical tests compared to comparing frequency. So these are the 5 questions. How many variables, how many groups, parametric or not, independent or not, mean or frequency counts. What is comparison of mean? You'll compare weight of one group with the weight of other group. There's no categorization here. 2 groups, that's it. You're not putting people into any further boxes. Only 2 groups are there. So you're comparing mean values. Okay. So keep those 5 questions in mind. So let's see what are the different tests that we have. T-tests. Students' T-test is the first test. When do you apply students' T-test? If you're comparing two groups, okay, and if you have a parametric observation, which is normally distributed, and if you're comparing mean values between 2 groups, and if you have independent observation. So in the example where I compare males and females, the age distribution of males and age distribution of females, that's a students' T-test. Okay. If the distribution is skewed for some reason, if it is not normal, then I will use non-parametric equivalent of students' T-test. What is that? That's called Mann-Whitney U. Okay. Students' T-test is unpaired, independent or unpaired. Okay. Independent means not paired, so you can call that as unpaired T-test. Students' T is also called unpaired T or independent T, and the non-parametric equivalent of students' T is Mann-Whitney U. So in Mann-Whitney U, you will satisfy everything: independent observation, mean value, 2 groups, but you will not satisfy the parametric assumption. So in that case, you will do Mann-Whitney U test. It's non-parametric. So whenever I give you a parametric test, I will also give you a non-parametric equivalent. Okay. So that's students' T and Mann-Whitney U. 2 tests done. Let's move to paired T-test. In paired T-test as well, you compare means between 2 groups, but same subject undergoes 2 observations. So this is comparing your group's mock exam score today and your group's mock exam score tomorrow. Same individuals are going 2 tests. Okay, so that's called paired T-test. So what is the so this is parametric. This is parametric. Remember, this is parametric. Paired T-test is parametric. All T-tests are parametric. Okay. So what is the non-parametric equivalent of paired T-test? Wilcoxon rank sum test. For students' T, non-parametric is Mann-Whitney U. U for unpaired. Remember that. For paired T-test, Wilcoxon rank sum is the non-parametric equivalent. So we have 2 tests now. Let's move on to ANOVA. Like T-test family, we have ANOVA family. ANOVA family is also called F-test family, F. So what are the types of ANOVA we have? We have one-way ANOVA. The term one-way stands for univariate. All of the T-tests are univariate, okay? But ANOVA, most of them are univariate, but some of them are multivariate, and I'll tell you what multivariate are as we go along. So at the moment, one-way stands for univariate ANOVA. One-way ANOVA is univariate ANOVA. ANOVA is used whenever you have more than 2 groups. You can also use ANOVA for just 2 groups. Nothing stops you from doing it. But usually we use ANOVA if we have more than 2 groups. Okay, so ANOVA, just like t-test, is a parametric test, and independent observations for one-way ANOVA, and mean is compared. Okay, so mean comparison, independent, parametric, more than 2 groups ANOVA. So what is the example? I'm going to compare the age of people who attend my online course, people who attend our webinar, and people who attend our face-to-face course. Okay, so 3 types of courses. I'm going to compare age of all the 3 groups. So how many groups do I have? More than 2. Age is a ratio data, is parametric. And independent observation, one person's age is not going to affect another person's age. And it's a mean value, mean age of the 3 groups. So I will now do one-way ANOVA. Okay. What is the non-parametric equivalent of one-way ANOVA? Kruskal-Wallis test. Kruskal-Wallis test is the non-parametric equivalent of one-way ANOVA. Now, what is the other type of ANOVA we have? Repeated measure ANOVA. The term itself tells you what it is. Repeated measure. The same metric is repeated more than once. So that's paired. Okay. So repeated measure ANOVA is the extension of paired t-test to 3 groups. So you have more than 2 groups, parametric, paired observation, mean value. So this is nothing but extension of paired t-test to more than 2 groups. Okay, that's called repeated measure ANOVA. And the non-parametric equivalent of repeated measure ANOVA is called Friedman test. I know it's hard, but you have to keep these things in mind. One-way ANOVA, non-parametric is Kruskal-Wallis. Repeated measure ANOVA, non-parametric is Friedman test. So that's about ANOVA. One-way stands for one variable, univariate. What is the multivariate equivalent of one-way ANOVA? It's called n-way ANOVA. If you have multivariate, if you are looking at more than one variable, if you are looking at 2 or 3 or 4 variables, or if you are looking at confounders, so that's called n-way ANOVA. If you are adjusting for confounders, the n-way ANOVA takes another name, ANCOVA. ANCOVA is same as n-way ANOVA, but this term is preferable if you are adjusting for confounders. Analysis of covariance. ANCOVA stands for analysis of covariance. ANOVA stands for analysis of variance. ANCOVA stands for analysis of covariance. Co, because it's co-occurring with something else, and that's the third factor, the confounding factor. So remember, ANCOVA is to adjust for confounders. It's an n-way ANOVA. Okay. So one-way means only one variable, n-way means more than one variable. And a special type of n-way ANOVA, ANCOVA, is used for adjusting for confounders. So now we have seen one multivariate test, which is n-way ANOVA. Everything else we have seen is only univariate. Okay, ANOVA is parametric. So whatever assumptions you have parametric, normal distribution assumption, will apply for ANOVA. ANOVA uses F statistics. Just like t-test, ANOVA is called F test. One of the problems with ANOVA is it's a beautiful test. You can compare multiple groups, 2 groups, more than 2 groups. You can compare any number of groups with ANOVA. But the result of an ANOVA only tells you if the groups are different or not. That's all it says. It says if the groups are same or groups are different. It doesn't tell you where the difference comes from. Does it come from the difference between groups 2 and 3, or 3 and 4, or 4 and 5? That you won't know when you do ANOVA. Okay. So to know that, to understand where the difference comes from, you got to do a post hoc test. Post hoc test. Post hoc tests are usually t-tests. So first you do ANOVA, find out if there is a difference or not, and then what you do a t-test to find out where is the difference coming from. So whenever you use ANOVA, you can use a t-test. Okay, the vice versa is also true. Whenever you use a t-test, you can use an ANOVA. So in your exam, in an EMI, if they ask you to choose an option for comparing 2 groups, and if you have already chosen t-test based on the information given, they ask you to choose one more choice, 2 choices, then you can choose ANOVA. Okay, so far we've been looking at mostly univariate test, mostly comparing mean values. Now we are going to look at a univariate or a multivariate test that compares proportions. Proportions means categories. You're putting people in boxes, 2x2 tables. So when you draw 2x2 table, 3x3 table, any table where you put people into boxes, cells, you're comparing proportions, and in that case you'll use very simple chi-square test. Forget about all other questions, number of variables, forget about groups, number of groups, and all of those things. Whenever you have a proportion comparison situation, you can use a chi-square test. Okay, there are 2 variants of chi-square that you have to keep in mind. One variant is called Fisher's test. When you draw a 2x2 table, you should have decent number in all the cells. If any of the cell has value, if at least one cell in a 2x2 table has value falling less than 5, then chi-square becomes unstable. Chi-square test becomes well, not dependable. So you will use a modification of chi-square. In that case, it's called Fisher's exact test. Fisher's exact is same as chi-square, but it is used when one of the cells in your 2 by 2 table has value less than 5. Okay. But 20% of cells in a 2 by 2 table, there are 4 cells. So 20% of cell means at least one cell. Okay, at least one cell having value less than 5 means you use Fisher's test. Another variation of chi-square is called McNamara. McNamara is used whenever you have to use chi-square for repeated measures. Okay, so let's say I am calculating proportion of people who pass mock exam today, and proportion of the same group, the proportion of people who pass mock exam after my teaching. Same group of people, 2 observations, so there's paired observations, but I'm looking at a proportion today and proportion tomorrow, and I'm comparing the difference in this proportion to see if it is significant or not. So I'll be using McNamara's test in that case. Okay, that's called repeated measure chi-square test. Okay, so far we have seen a number of tests: T family, F family, and we've also seen chi-square family. Now we are moving to bivariate statistics. Bivariate means you are interested in relationship between 2 variables. What are the 2 variables you are usually interested in? Cause and effect. Okay, let's say I have a relation. I want to see what is the relationship between hours that you sleep and body mass index. So I have 2 variables. Sleeping hours can vary between, I don't know, 2 to 12. So it can take any value between 2 and 12. And body mass index, again, it can take any value. So I'm going to relate these two. So two variables, when I relate them to each other, that's called bivariate analysis. And in this case, I will do a correlation analysis. So how can you test the significance of correlation? You can use either Pearson's correlation coefficient or Spearman's correlation test. Pearson is used when you have 2 continuous variables. Both of them are parametric. So age and height, body mass index and sleeping hours. These are both biological, both are continuous. So we can take them as parametric data. We can use Pearson's correlation. If one of the variable that you put in a scatter plot, the correlation plot, if one of the variable is non-parametric, if one or both of them are non-parametric, then you will use Spearman's correlation. Pearson correlation is denoted by R. Spearman correlation is denoted by rho, the Greek alphabet rho. Okay. Both these values can vary between -1 to +1. -1 means perfectly linear negative correlation. In other words, when you sleep more, your body mass index becomes less. More the sleep, less the BMI. That means it's -1. +1 means there is a perfect positive linear correlation. More the body mass index, more the sleep is. More the sleep is, more the body mass index. That means it's +1. 0 means there is no relationship between the 2 variables that you are plotting. Okay, so that's called, this is the range of correlation coefficient, -1 to +1. Okay, remember, just because 2 things are correlated, that doesn't mean one causes the other. Okay, the correlation could be spurious. Sleep hours may not have anything to do with BMI. Okay, and there's a reverse causality also possible. So correlation does not mean causation. It's an important important index for causation, but it doesn't sufficient. It's not sufficient for suggesting causation. Okay. Now kappa. Sometimes we use another bivariate metric called kappa. Kappa is a measure of agreement, not association. What's kappa? I will see what kappa is in a minute. In this table you will see what kappa is. Let's say I have a trainee with me. I'm a consultant and I have a trainee with me, and we have 5 people coming to our clinic, one after the other, 5 consecutive patients, and we are using a scale to see how many symptoms these patients are endorsing in the scale that we use. My trainee scores, for the one patient A, my trainee scores 7 items and I score 7. Second patient, my trainee scores 8, I score 10. She scores 2, I score 2. She scores 4, I score 3. She scores 12, I score 15. Now can you see, broadly, we both are both of our scores are in association with each other, because she scores 2, I score 2 as well. She scores 15, I score 12. Okay, so if she scores high, I score high as well. And so that if you plot both of our scores, you will see there is an association. If I score high, she scores high as well. This is trainee symptom, this is my symptom count. So there is an association. But how many times do we agree with each other? Agree is exactly the same result, categorical result. Only 2 times. 2, 7. Only 2 times we agree with each other. But we have an association. Okay, so that's the difference between association and agreement. Association is a continuous metric and you can represent that by using correlation coefficient, but agreement is a categorical metric and you represent agreement using kappa. Kappa is used for categorical nominal agreement. Okay, now kappa less than 0.2 is poor, greater than 0.6 is good. Kappa can vary between 0 and 1. Less than 0.2 is poor agreement, greater than 0.6 is good agreement. Kappa depends on prevalence. If you're looking at something that's commonly present, then both of you will agree with each other more often than not. Okay, but if you're looking for a rare event, then kappa will be low. So the mathematical formula for kappa is actual agreement beyond chance divided by potential agreement beyond chance. Now in your exam, remember, they will not ask you to calculate kappa because this is a complex metric. They'll only ask you some basic understanding about kappa. Do you understand that it is for nominal data? Do you understand it is for agreement, not association? Do you know what are the conventionally acceptable values for poor kappa and good kappa? And do you know how it is derived? It's derived using a fraction between actual agreement and potential agreement beyond chance. Okay, so that's kappa. So we have seen kappa. Let's go back to other bivariate statistics. So we have seen Pearson, Spearman, and kappa. Let's see regression. Now regression can be bivariate or multivariate. Let me just first talk about bivariate regression. Regression is one step further from correlation. In correlation, I was trying to predict somebody's BMI using sleep hours. Okay, I was trying to relate BMI to sleep hours. Let's say if I want to predict somebody's BMI, I want to know how much BMI someone has, exact value of the BMI, by measuring other variables. Okay, I want to predict the exact BMI value by using other variables such as sleep hours. Do you think sleep hours would be sufficient to predict somebody's BMI? Probably not. Let's say it works that way. Let's say if it works that way, how can I make sure it works that way? I should be able to draw a linear regression equation. Y, which is BMI, is equal to A, some constant, plus B, regression coefficient. B is regression coefficient multiplied by X. X here is sleep hours. So if I'm able to draw such mathematical equations for a given value of X, if I know those constants A and B, I can determine what the Y would be. If I could put issues in such equation, then I have managed to predict Y from X. I'm managing to predict the dependent variable Y from the independent variable X. I'm reducing the relationship into a mathematical equation. This equation is a linear equation because you have an equal to sign here and you don't have any logarithm or any exponents here. So this is a linear regression with just two variables, Y and X, bivariate linear regression. So I already told you that sleep hours X may not be sufficient to predict Y here, BMI. So let's say you add X and you add X1 as sleep hours, you add X2, which is the amount of calorie people take, X3, the amount of exercise people do. Okay, hours of exercise and amount of calorie consumed. Now this equation may be a better predictor. Okay, so if you have this kind of equation where one dependent variable is predicted by multiple independent variables, this is called multiple regression. This is also linear because there's an equal to sign, there's no logarithm. Okay, so this is multiple regression. First example is linear regression, simple linear. This is multiple regression. When can you use multiple regression? You can use multiple regression if you have multiple independent factors or if you have a confounding factor and some independent factors. Let's say X1 is a confounder, X2 and X3 are independent causal factors. In this condition where you have confounders, you can use multiple regression because it's a multivariate statistics. All multivariate statistics can be used for looking after confounders. So now we have seen two equations, linear and multiple. What is this? Y is equal to A plus logarithm of X. This is called logistic regression or ordinal regression. This is used if one of the variables that you are dealing with is non-parametric or ordinal. Okay, so let's say X here is an ordinal variable. What is ordinal? Ordinal means it has order. It doesn't have a quantifiable number. It's not a quantifiable number. It's only a ordinal value. Let's say I'm trying to represent somebody's, I'm trying to predict somebody's BMI using their blood group. Blood group is not a metric. It's only an ordinal observation. So in that case, I will use log. Okay, so logistic regression. This is a condition where you use ordinal. So if you're predicting outcomes, let's say Y is a binary outcome, whether you develop a disease or not. That's Y. If that binary outcome is predicted by a number of other factors, again you can use logistics. Okay, so logistic can be used whenever at least one of the variable is non-continuous. Either it's ordinal or it's binary. Binary means categorical. Okay, so those are the conditions where you use regression. Remember, A stands for a constant, it's called intercept. B stands for the regression coefficient. Just like how you have R and rho in correlation, called correlation coefficient, in regression the coefficient is called regression coefficient and it is represented by B. Sometimes people use beta. So if you see B or beta, that is a regression coefficient. So we have seen some multivariate techniques already. What are they? We saw multiple regression and we saw ANCOVA. Both of them are multivariate techniques. You can also have other multivariate techniques like factor analysis, discriminant function analysis, cluster analysis, path analysis. Okay, so remember the names of these things. They don't ask you a lot of details about them. Of these, factor analysis is interesting. We use factor analysis if you have a lot of data. If you have loads of data and you want to reduce the data to meaningful factors, small number of factors, you will use factor analysis. Okay. When do you use path analysis? Path analysis is used when you want to examine the chains of causation. What do I mean by chains of causation? In science, well, in real life, you rarely have a single factor A causing a single factor B. A may cause B, B may cause another thing called C, and C indeed may be causative for A, so on and so forth. So you usually have a web or a chain of causal influences. Let's take the example of poverty, socioeconomic status, depression, and suicidality. Poverty, poor socioeconomic status can cause depression, and that can cause suicidality. Depression can also cause poverty because you can't work very well. Poverty itself can directly cause suicidality without having any depression. So there are multiple chains of causation. If you want to analyze those multivariate chains of causation, you use path analysis. So remember the phrase chains of causation for path analysis, reducing or categorizing data for factor analysis. Okay, so that's all about major statistical tests. So we have seen t-tests, f-tests, we have seen chi-square tests, we have also seen correlation family, we have seen regression family. So those are the 5 families: T family, F family, chi-square family, correlation family, regression family. Now I'm showing some tests which we used for control for multiple testing. Do you remember I said whenever you do repeated testing on the same sample, you will end up with doing type 1 error. So how can you reduce type 1 error? How can you reduce type 1 error? You can reduce type 1 error by correcting for it statistically. The correction commonly is called Bonferroni correction. Okay, Bonferroni correction is a statistical test used for adjusting for type 1 error. Okay, you also have other statistical tests for correcting for type 1 error. What are they called? FWE, family wise error test, Chef's test. This is not Turkey, it's Tukey. Tukey's honestly significant difference test. Yeah, it's called honestly significant difference test. You also use FDR, false discovery rate. All of these are control for multiple testing. We have seen kappa. Okay, so we also see survival analysis. What is survival analysis? So far, we've been looking at univariate, multivariate statistics where the variable is some event or some measurement. Sometimes the variable of interest is not the actual event. It is the time it takes for the event to happen. So let's say you're interested in response as an event. So you have 2 groups, one group taking olanzapine, one group taking placebo. You want to see how many people respond in olanzapine group and compare it with how many people respond in placebo group. In this example, response is the event of interest. So you can use chi-square test if you want to compare the proportion of responders in the 2 groups. If your interest is not actual proportion of responders, if your interest is how long it takes to respond in olanzapine group compared to placebo group, if time is the variable of interest, then you will do something called survival analysis. Okay, to do survival analysis, you need to plot curves, survival curves. These are called Kaplan-Meier curves. Kaplan-Meier curves are nothing but survival curves. So you put time along the x-axis and proportion surviving your outcome along the y-axis. So this is a Kaplan-Meier curve. So you have days in treatment, time along the x-axis. On the y-axis, proportion of people who survived the treatment or retained in the treatment, people who did not drop out. That's called proportion retained, proportion surviving the outcome. That's put on the y-axis. Remember, it's called survival curve. You don't plot the probability of the bad event. You plot the probability of surviving the event. Okay, so probability of survival is 1 minus the probability of the event is survival. if there are 100 people and 90 die, how many survive? 10. Okay, so 1 minus the percentage of survival, or the percentage of 1 minus the percentage of event gives you the percentage of survival. That's what you put here. Okay, the proportion surviving goes on the y-axis, probability of survival. Okay, so that's a Kaplan-Meier survival curve. How do you compare? What statistical test that you do to compare the two groups? So now in this Kaplan-Meier curve, I have two groups. This first group is the BPN group, it's taking bupropion. Second group is carbamazepine group, CBZ group. So I have CBZ group and BPN group. If I want to compare if these two groups are statistically significantly different, well, if you look at them, they look different visually, but are they statistically different, statistically significantly different? To answer that question, I can do a log rank test, statistical comparison of survival rates, log rank test. I will also do a Cox regression analysis if I want to compare the two groups for their survival, but after taking into account confounding factors. So Cox is confounder controlled comparison of survival rates. So in that case, I will do Kaplan-Meier. In that case, I will do Cox regression analysis. Okay. So far we have seen different types of statistical tests. What are the 5 questions to ask? T-test, ANOVA family, chi-square family, correlation family, regression family, some names of multivariate statistical tests. We have seen what kappa is, and we have also seen Kaplan-Meier survival. So finally, I will also take you through reliability and validity. Now it's a slightly different topic. This is not about comparing groups. This is about looking at a diagnostic test and deciding if the test is useful or not. So if you have a diagnostic test instrument, how do you decide if it's useful or not? The instrument should be reliable, and it also should be valid. Reliable means every time somebody does that test with that instrument, they should get the same result. Replicability is the same as reliability. Okay, so what about validity then? Validity refers to applicability. Validity refers to whether the diagnostic test, the instrument that you have at your hand, is that going to measure the construct that you really want to measure. That's called validity, applicability. For example, if you have a depression scale, is it really measuring depression? If it does, then it's a valid scale. If it is not, then it is not valid. So that is validity. Validity is how truthful your scale is. Reliability is how repeatable your scale is. There are various types of reliability. There are various types of validity as well. So let's first look at the different types of reliability. Test-retest reliability. Test-retest reliability is, let's imagine you have a sample of people. You want to measure how much they are depressed, and you use a depression rating instrument. If you use a rating instrument that has good reliability, good test-retest reliability, then if you use that instrument on the same sample on 2 different occasions, not too different in time point, but just close to each other. Let's say you measure now and you measure 10 minutes later, then you should have same kind of score from the same set of individuals. If that is true, then you have good test-retest reliability. What about Cronbach's alpha? Cronbach's alpha is called internal consistency of a test. It's also a measure of reliability. Let's say, well, in each scale that you use, you will have an item score and you have a global score. Internal consistency refers to how each individual sub-item score relates to the global score. For example, in Hamilton depression, you have items like suicidality, hopelessness, so on and so forth. If whenever Hamilton depression overall score goes up, if scores in suicidality and hopelessness also go up, that means there is a good degree of internal consistency. Now, the mathematical measure of internal consistency is given by Cronbach's alpha, and that varies between -infinity to +1. The maximum value is +1, and the minimum value it can take, the least value it can take, is -infinity. So remember that, because that has been tested in your exam in the past. Then split half reliability. What is split half reliability? The name itself tells you what it is. If you take a scale and you split it into 2 halves, then the amount of scores that you get from one half should relate to the amount of scores that you get from the second half in the same sample at the same time. So if you take Hamilton depression scale and you tear it apart into 2 pieces, part A and part B, then part A scores should correlate with part B scores. If it does, then it has good split half reliability. The test is reproducible even if some items are missing. That's what it means. Then comes inter-rater reliability. What is inter-rater reliability? You have 2 raters rating the same sample at the same at same point of time, more or less same point of time, but 2 different raters. Let's say you and your trainee, or you and your consultant, you are rating the same set of patients on Hamilton depression. If both of you have same set of observations made, if both of you have good correlation in your scores, that means you both have good inter-rater reliability. So the reliability between two raters is inter-rater reliability. Reliability between two different tests done by the same rater is test-retest reliability. So these are the 4 types of reliability. What about types of validity? The simplest type of validity is phased validity. You look at the scale, just examine the scale, look at it, and tell if the scale looks like it's measuring depression. So Hamilton depression scale, if you look at it, what can you see? You can see it has items of suicidality, hopelessness, so on and so forth. So it is a scale that subjectively appears to reflect the construct that underlies it, depression. So you can say Hamilton depression scale has phased validity for depression. So phased validity is just superficial examination. Look at it and say what it looks like. Okay, but that's not good enough for statistics. We have to go deeper. Construct validity. Construct validity is examining the deeper construct that comes out of the measurement. So again, construct validity is of 2 types, content and criterion. Content validity is you give the scale to a set of experts. You ask them to look at each and individual item in much more methodical detail, and you ask them to see if those items really reflect the construct that is supposed to be present. So let's take Hamilton depression, HAM-D21 for example. HAM-D has 2 versions, 21 and 17. The 21 version has 21 items, 17 version has 17 items. What are the items missing in 17? You don't have obsession, you don't have paranoia. So when experts examined the HAM-D21, they were able to say that contents such as paranoia are not really reflective of the construct of depression. They are reflective of something else like psychosis. So they removed those items that improved the content validity of Hamilton depression scale. So HAM-D17 has slightly better content validity than HAM-D21. So that's what experts do. They examine each and individual item and determine the validity. What about criterion validity? Criterion is much more statistically minded test. So you have 3 types of criterion validity. Criterion means you are comparing your scale with some standard. If that standard is an external standard concurrently applied, then that's called concurrent validity. So you can compare HAM-D with BDI, Beck's depression. Then you will be establishing external validity of HAM-D. You can also have predictive validities. You can test your scale against something that will happen in the future. So if HAM-D score is high, then the patient must have higher risk of self-harm in the future, because depression predicts self-harm. So that's called future validity. That's called predictive validity. Concurrent is examining a criterion that can be applicable at the same time. Predictive is examining a future criteria. Incremental validity is looking at what has been done in the past. So looking at what is being done currently or done in the past, and see how your scale can provide an increment or improvement in what is already being done. So let's say the current practice of diagnosing, establishing severity of depression is based on the DSM-5 criteria. If you have 7 symptoms, you have severe depression. If you have 5 symptoms, you have moderate depression. So that's the current practice. Examine that practice against using something like HAM-D or BDI. See if those scales add anything more than what you already achieve with current practice. If your scales do, if they give you something more than what you currently do, then you can say your scales have incremental validity. Incremental validity is very important if you want to sell your product. If you want to sell your scale to other people, you have to show there is incremental validity. These are 3 types of criterion validity. Psychologists sometimes talk about convergent and divergent validity. Convergent is 2 scales that are similar to each other should agree with each other. So Hamilton depression and Beck's depression, if you apply to the same group of people, their scores must converge. Whoever scores high on BDI should also score high on Hamilton depression. So that's called convergent validity. If you're examining 2 different constructs, 2 different scales, measuring 2 different constructs, let's say Young's mania scale and Hamilton depression scale. So if you apply those scale to a same set of people, let's say all of them are depressed, then people with high score of Young should have low score of HAM-D, and people with high score of HAM-D should have low score of Young's, because these are 2 opposite divergent constructs, mania and depression. So if you establish that kind of divergence, then what you're testing is called discriminant validity or divergent validity. These are also other types of measuring construct validity. Okay, let's see some questions now. Okay folks, let's see some questions now. Question 18. Which of the following with regard to correlation coefficient is incorrect? It's a measure on a scale of -1 to +1. Describes the degree of association between 2 variables. A positive value implies that a rise in one variable accompanies rise in the other. It's demonstrated by the symbol kappa. Spearman's correlation coefficient is a non-parametric method of deducting correlation coefficient. Okay, so of these, the false statement is kappa, because you know kappa represents agreement, not association. Spearman's is denoted by rho, Pearson is denoted by R. The maximum value that can be attained by Cronbach's alpha, you know what Cronbach's alpha is, it's internal consistency. The maximum value is +1 and the minimum value is -infinity. So the answer is C, +1. Goodness of fit between two or more variables can be tested using which of the following statistical methods. So you're fitting one value to the other and you fit through equations. So goodness of fit is measured between two variables is measured using regression. So when you see the term goodness of fit, you're trying to fit some sort of mathematical equation between dependent and independent variable. So that's regression. And the goodness of fit is usually used for two variables. So it's a bivariate regression, simple linear regression, for example. B is the right answer. Which of the following statistical tests would you use when comparing two groups to compare the risk of committing suicide after engaging in two different methods of self-harm? Chi-square, Kruskal-Wallis, kappa, Cohen's d, Student's d. So because this is risk is a proportion, you will choose chi-square test. You can go methodically asking how many groups, how many variables, what kind of metrics are you using, parametric or non-parametric, but all of this is trumped by the issue of proportion. So whenever you compare proportions, you can only choose one family of tests, and that's chi-square. So chi-square test is the answer. Which of the following test is a non-parametric equivalent of comparing two means using t-tests? So now we have two groups, two means are being compared. So they're asking you what is the non-parametric equivalent of comparing two means using t-tests. They're not telling us whether it's unpaired or paired t-test, but let's just see what is given here. We have Mann-Whitney U-test. We don't have the rank sum. We have Wilcoxon test written here. We don't have any other option that is non-parametric. Well, chi-square is not applicable. Kruskal-Wallis is for non-parametric ANOVA. Spearman is correlation coefficient. So because there is no information given about paired or independent, let's just assume this is independent, because without any information you can't assume it's paired. So let's just assume that this is two different means. So it's unpaired t-test. For unpaired t-test, the equivalent would be Mann-Whitney U-test. If you lack information, just go by default. Okay, so default is usually independent t-test. Which of the following is a multivariate technique? MANOVA, path analysis, cluster, factor analysis. All of the above. Yes, all of the above is the right answer. Which of the following methods can be used to correct for multiple testing in a dataset? Born-Ferroni correction, increasing p-value, Cohen's kappa, scatter plotting, none of the above. So multiple testing correction can be done using Born-Ferroni. What other tests do you know? Yeah, false discovery rate, 2 keys, honestly significant test, Schiff's test, so on and so forth. But the most commonly used is Born-Ferroni correction. A cohort study observes a number of myocardial infarctions developing in patients on olanzapine. If the study runs for a 5-year period, there may still be few myocardial infarctions that may occur after 5 years. Such unobserved data in survival analysis is called dropout, attrition, violated data, censored data, hazard data. This is called, so look at this Kaplan-Meier here. Let's assume this is a group. You're observing this group for 10 days and some events are happening. So every step that you see in Kaplan-Meier curve is a time when some events of interest happens. So this is when some events of interest happen. So you drop the curve. And can you see the curve never comes to the bottom? It stops somewhere here, 10th day. Does it mean nobody else develops any events? So if you extend this curve like this, does it mean nobody else is going to have any steps after this? No, some people will, but you can't indefinitely continue a study. You have to stop it at some point. So after this point, there may be some events happening, okay, but we are censoring it. So this is called censored data. You can't really see the events that happen after a point of time. So this is called censored data. A jubilant psychiatrist, after passing final MRC Psych exams, wants to examine the validity of MRC Psych paper 3 theory exams. Well, you can say paper B now. She chooses to examine the degree of association between paper B scores and CASC clinical final exam scores. Which of the following is she testing? Convergent validity, divergent validity, predictive validity, phased validity, content validity. So the question is, does paper B scores, do they have any predictive validity when it comes to CASC exam scores? So that's the question here. Future CASC is going to happen at a different point in the future. If your scores now predict your scores in CASC, then the MRC Psych paper B scores have high predictive validity. What do you guys think? Do you think there is a predictive validity for paper B scores? Okay, so let's just go to next question, MCQ 27. A depression rating scale A gives a score of 10, 12, 14, 11, 12 when used in the same patient by different raters. A different scale B gave values of 28, 7, 6, 29 and 16. When a gold standard test is used, the depression score was equal to 12. So the truth is 12. The first scale observes 10, 12, 14, 11 and 12. Second scale observes 28, 7, 6, 29 and 16. Choose one right statement. Scale A is very precise but not accurate. It looks like scale A is precise. The values are close to each other. And it's also accurate, okay, because it's close to 12. Okay. Scale B is accurate, not precise. Scale B is not precise, clearly. The range is 6 to 29, so it's a huge range, 23 points. And it is not close to 12 as well, so it's quite inaccurate. Scale B is both precise and accurate is wrong. Scale A is both precise and accurate is the right answer. Scale A is both precise and accurate. 28. You're comparing means of two sets of scores which are repeated observations on same group of individuals. So two sets of scores and they are repeated observations. The scores are normally distributed. Which test would you use to compare this? Let's assume this is parametric because they are not telling us not giving us any information. So remember, by default, if they don't give you any information, assume it is normally distributed. Okay. Because parametric tests are always much more preferable than non-parametric statistical tests. So what would you do here? Same group of individuals. So everybody is being observed twice on the same value. So this is going to be a pad t-test. Okay, so the answer is B, pad t-test. Using scale for negative symptoms of schizophrenia, an investigator measures rating on 34 different symptoms and signs. He wants to aggregate them into few meaningful groups by analyzing the degree of correlation between different variables. Which of the following test is best suited? So you're going to aggregate data into few groups. So you're reducing data into small number of factors. This is called factor analysis. Okay, multivariable because multiple variables because 34 different symptoms and signs. So multivariate test. Factor analysis is a multivariate statistical test. Questions 30 to 32. 30. 120 adults of working age receiving input from a community mental health team in North Yorkshire invited to complete carers and users expectation of services user version questionnaire. The 16-item self-rated outcome measure covers the issues that both using mental health services have identified as being their priorities. Total satisfaction scores for patients according to the psychiatric diagnosis are shown in the figure below. So this is the total satisfaction score. What type of graph is this? Yeah, you know the answer for this. This is box whisker plot. Okay. The upper and lower horizontal edges of the shaded area. So this is the shaded area. Upper and lower horizontal edges. They refer to what? They refer to the interquartile range. Okay, so that's the interquartile range because this is the 25th percentile value, this one, and this is the 50th percentile value. So this is, sorry, 75th percentile value. So this is interquartile range. Okay. Dark line across the box. Usually this is median. Okay, so this is usually median. So MCQ 33, in 2007, 20 patients working at a car factory presented to a GP with non-specific symptoms. GP suspects that males have more clinical symptoms of lethargy, cognitive impairment, loss of libido, consistent with lead intoxication. She recorded the urine lead level, which reads as follows. So they've given urine lead levels for males and females. Okay, so a lot of numbers are given here, and a lot of numbers are given here as well. The best way to analyze the data, so you've got to compare males versus females. If they have more, if males have more lead in the urine compared to females. So what test can you do to establish the significance of difference? Males and females are two different groups. Two groups, only one variable, lead, two different groups. Okay, so independent, and it's going to be a mean value that you're comparing because this is a normally distributed. This is a biological metric. So you're going to compare mean. You're not categorizing people into groups here. So only two groups are there, males and females. You're not further dividing them into any subgroups like responders, non-responders, so on and so forth. So what test would you use? Two groups comparing, yeah. Would you use t-test or would you use Mann-Whitney U? So the option is either unpaired t-test or Mann-Whitney U. Both of these can be used. What would you use? What is the deciding factor? Whether the distribution is parametric, normal or not. Is the distribution normal? How do you know that? Okay, well, if they don't give the data, then you can assume lead is normally distributed, but here the data is given. So have a look at the data. Can you see there is an outlier here? Huge outlier, 211. Some people have 3 very small values, and this person has very large value. Okay, so this is an outlier. Outlier is going to skew the data. When the data is skewed, you cannot use paired t-test. Unpaired t-test. You cannot use t-test for skewed data. So you'll only use Mann-Whitney U-test, and that's the right answer because it's non-parametric. Mann-Whitney U-test. 2 different techniques of dialysis are being evaluated for side effect profiles. Type M uses membrane filter, while N uses non-biomembrane filter. Dialysis-related cognitive impairment is assessed as the outcome of interest. Of 40 subjects in M group, 16 had symptoms of cognitive impairment compared to 12 out of 45 on type N. So now you are counting people, you are putting people into boxes. Cognitive impairment present or absent. So which test can be used to test the statistical significance? T-test, chi-square, Mann-Whitney U, Fisher's, or one sample? You'll use chi-square test. Okay. So before you choose between chi-square and Fisher's, the question to answer is, would each box will have more than 5 observations? So out of 40, if you take 16 away, the remaining will be 24. So that's greater than 5. Out of 45, if you take 12 away, the remaining will be 33. So that's also greater than 5. So you can happily choose chi-square test. You'll be fine here. Chi-square test. Same question, slightly altered here. So 2 different types of dialysis, M and N. Dialysis-related cognitive impairment is assessed. Of 10 subjects on type M dialysis, 5 had cognitive impairment. So now you can see 10 subjects are on M, 5 had cognitive impairment, and the remaining box will have only 5. And only 1 out of 8 on type N has cognitive impairment. So 1 is a number smaller than 5. In this case, the statistical test cannot be chi-square because it is not robust when values are very small. So you will use Fisher's exact test. D will be the right answer in this case. A standard normal distribution is characterized by which of the following? So you know what a normal distribution is. Mean is same as median is mode. What is a standard normal distribution? A standard normal distribution is nothing but a normal distribution where mean is equal to 0 and standard deviation is equal to 1. So remember that. If the mean is 0, standard deviation is 1, that's called standard normal distribution. Okay. Next question. What curve is this? Yeah, you know what this is. This is a Kaplan-Meier survival curve. So an open label observation study of patients undergoing opioid detoxification using buprenorphine valproate. So this is BP and VPA is buprenorphine valproate combination. And then you have clonidine carbamazepine combination. Clonidine carbamazepine. So this is clonidine carbamazepine. This is buprenorphine valproate. So this is comparison was conducted for 12 patients in this group and 50 patients in this group. Primary outcome of interest was a retention in the detoxification program. How many people stay in the program? That's what you're interested in. And now you have a Kaplan-Meier curve. This is proportion retained in the treatment. So people are dropping out slowly, one after the other. There is more dropouts in clonidine group compared to the buprenorphine group. You will expect that, right? Because buprenorphine is an opioid. More people will continue to take opioid. But clonidine is not an opioid. Carbamazepine and clonidine have no potential to give people the sense of taking opioids. So there are going to be more dropouts here, and that's what you see here, more dropouts in the blue group. The above curve, so answer the following questions using the graph. Which of the following best describes the graph? You know the answer for this, it's Kaplan-Meier curve. Last observations for this study were made on completion of how many days of treatment? So when was the last observation made? 0, 1, 2, 3, 10 days. So answer is 10. Last observation were made on the 10th day. Proportion of the BP and VPA group that stayed in the detoxification program at the end of the observation period. So proportion that survived, stayed at the end of the observation period. So extend this number, extend this here, you'll see something like 0.7. So the probability of survival is nearly 70%. Okay, so that's the answer, nearly 70%. 0.7 is 70%. Okay, so 1 is 100%, 0.7 is 70%. Answer is nearly 70% stayed in the detoxification program for the BP and VP group. What about the blue group, clonidine group? Around 50% stayed in the treatment by 10 days. Which of the following tests can be used to analyze the significance of difference between the two groups? So if you want to compare blue group and red group, what test would you use? You'll use log rank test. Okay, log rank test. Let's now go to EMI1 statistical test. Question 1. 22 patients with chronic PTSD were treated with naltrexone, and mean score of hyperarousal and avoidance symptoms were compared before and after 6 weeks of treatment. Okay, so there's one mean score that you are comparing. mean score on hyperarousal and avoidance symptoms. Okay, so you're interested in one variable. How many groups do you have? 2 groups. One group before treatment, the other group after 6 weeks of treatment. So before and after design. So the observations are paired here. Okay, so what test would you choose? You can choose paired t-test 7. Paired t-test will be the right answer. Okay. In the Helsinki high-risk study, the proportion of high-risk offspring who developed, so proportion, look at the keyword here, proportion of high-risk offspring who developed soft signs was compared to the proportion who develop of control, proportion bound to control mothers who develop them. So choose 2 options. So you can choose chi-square because it's a proportion. Because they're insisting for you to choose one more option, you can choose well, fishes. Whenever you choose chi-square, you can also choose fishes. These two go hand in hand. Okay, 5 and 6. 3. Serum epidermal growth factor levels were compared between subjects with high functioning autism and controls. The mean value of EGF was found to be significantly lower in patients. The pattern of distribution of EGF in general population is not known. So when they say the pattern is not known, they're telling you that they have some reason to suspect the pattern may not be normal. Okay. Well, most biological variables are normally distributed, but if they specifically state something about distribution, it is not known, which means they ask you to be conservative. So assume it is not normal. Okay. So how many groups do you have? Autistic group, control group, 2 groups, and you're interested in one variable, EGF, and you're comparing mean EGF in one group with mean EGF in another group, and you would assume it's non-parametric. So unpaired t-test non-parametric equivalent would be Mann-Whitney U test. Okay, so you'll choose the answer as Mann-Whitney U. So for this one, option is G. Well, A, B, C, D, E, F, G, paired t-test. For this one, option would be E and F. E is chi-square. So E is fishes, F is chi-square. Okay, so you'll choose these 2. Option A for the Mann-Whitney U test for the epidermal growth factor question. So next question, multivariate techniques. Now choose one option from each of the description below. A researcher wants to analyze the various chains of influence existing among poverty, isolation, unemployment, depression, morbidity. So chains of influence, you will choose path analysis, H. A researcher wants to predict the value that a dependent binary variable can take using an independent variable and a constant. Predict means regression. Okay. And what are you predicting? You're predicting some binary variable. So you should use logistic regression, F. Within subject analysis for paired observation. So it's paired observation of mean. So mean value in 5 different groups. So let's assume we have one variable. We have 5 groups. What would you choose? Some kind of ANOVA, but it's a repeated measure ANOVA. So you'll choose D, repeated measure ANOVA, because it's the paired observation. Okay. So option D for the last one. Option F, logistic regression for second one. And option H, path analysis for the first one. Okay. Third question. A researcher wants to assess the strength of association between educational attainment rated as a continuous measure and degree of compliance rated as a continuous measure. 2 continuous measures, strength of association, bivariate. You will choose Pearson's test, Pearson's correlation coefficient, J. A researcher wants to compare the proportion of smoking psychiatrists and non-smoking psychiatrists in a local hospital who has been off sick at least one day in the last 28 days. So 2 proportions you are comparing. Okay. So you will choose chi-square test. Degree of agreement and reliability between 2 raters for nominal measures. Nominal measures, agreement, kappa. Okay, so kappa. J for first one, which is Pearson test. A, chi-square for the second one. And C, kappa for the third one. Now let's talk about sampling methods. An addiction psychiatrist is keen to investigate the effect of DVLA warning. DVLA is Driving Vehicle Licensing Authority. So DVLA warning on heroin users. He identifies 4 regular patients in his methadone clinic as suitable for the study and distributes copies of screening questionnaire through them to other heroin users known to drive a car. So you recruit one person, and through that person you recruit more people. What kind of sampling is this? This is called snowball sampling. Snowball sampling. Number 2, in order to study the amount of over-the-counter use of analgesics in depressed patients, first 50 consecutive patients attending outpatient clinic are screened. So you are taking a convenient, easy sample, first 50 people. Okay, so that kind of sample is called convenient sampling. More specifically, this will be called consecutive sampling. But because it's easy for you to do, it's called convenient sampling as well. So convenience is something easy to do. So first one option is C, snowball. Second one option is G, convenient sampling. Third question, in order to study the amount of over-the-counter use of analgesics in depressed patients, A questionnaire is sent to every 10th patient. If you capture every nth patient, n could be 5, 6, 7, 8, 9 or 10, any number, every 10th patient, if you capture every 10th patient in a list, then what you're doing is called, yes, systematic sampling. So F is the right answer. 4. In order to study the amount of over-the-counter use of analgesics in depressed patients in an outpatient registry are grouped by sex, age, older or younger, presence or absence of a history of analgesic prescription. A random sample is picked from each group. So you're stratifying people into subgroups and then you pick a random sample. So this is called stratified random sampling, B. Okay. Fifth question, in order to study the amount of over-the-counter use of analgesics in depressed patients in an outpatient register are grouped by sex, age, and presence or absence of a history of analgesic prescription. Then you're not picking them randomly. In this case, what you're doing, first 10 patients from each group are picked. So it's like a quota. People are divided into groups and each group has a quota. How many people in each group can come? 10 people can come from each group. So this is a quota sampling. This is called quota sampling. So F for the first one, which is systematic sampling, B for the second one, which is stratified random, I for the third one, which is quota sampling. Okay, so some more questions, some more EMIs on statistical tests. There's a scenario here. Hyperglycemia and metabolic syndrome are associated with the use of antipsychotics. A researcher wants to investigate this phenomena for the newly marketed antipsychotic paliperidone. He has various options with respect to study designs. For each design below, choose one appropriate statistical test from the above list. So first question, mean rise in glucose level after using antipsychotic paliperidone for 8 weeks in a sample of 50 inpatients. So you have 50 patients, okay, and what are you comparing? Before and after. Okay, how much rise takes place after 8 weeks? So you're comparing before and after, only one variable, glucose level, univariate. Assume it's parametric because they're not telling you anything different. So assume it's parametric because all biological variables are parametric. So you have normally distributed single variable, you're interested in mean values, and you have a paired observation. So you do a paired t-test, B. Next question, mean change in glucose level after using antipsychotics for 8 weeks in a sample of 50 inpatients taking antipsychotic paliperidone compared to 33 patients attending day unit for the same period of time. So now you have two different groups and you have mean value in one group, mean change value in one group and mean change value in another group. So you can take the baseline value of glucose and the 8th week value of glucose and you can subtract one from the other. You will get a change value. So now you have only one variable of interest. What is it? Change. Okay, and you're comparing two groups for the mean change. Now what kind of test would you use here? Assume it's also parametric because still you're dealing with glucose. So you will use, yes, you will use 2 sample T or unpaired T or student's T. So it's called I here, choice I, unpaired T test, student's T test. Okay, increase in prevalence of metabolic syndrome in a sample of 50 inpatients after using antipsychotic paliperidone for 8 weeks. So now you're looking at prevalence. What is prevalence? Is it mean or is frequency count? It's a frequency count. Okay, so increase after 8 weeks. So you have one group, well, one set of people, 50 inpatients. You're comparing the proportion before with the proportion after. You could use chi-square test, but much more useful for you would be McNemus test, because whenever you have repeated proportions, comparison of repeated measured proportion, you can use McNemus test, H. Finally, comparing prevalence of metabolic syndrome in a sample of 50 inpatients after using antipsychotic for 8 weeks and sample of 33 patients taking psychotherapy. So you have two different groups. You're comparing proportions in two groups, chi-square test. Okay, so this is chi-square test. Option H for this one, McNemus. Option A, chi-square for the other one.